Heisenberg's uncertainty principle stands as one of the most groundbreaking concepts in modern physics, fundamentally altering the trajectory of scientific thought in the 20th century. In 1927, Werner Heisenberg, a German theoretical physicist, introduced this principle, which has since become a cornerstone of quantum mechanics. At its core, the uncertainty principle asserts that there is a fundamental limit to the precision with which certain pairs of physical properties of a particle, such as position and momentum, can be known or measured simultaneously. This idea challenges the classical worldview of determinism, where one could predict the future of a system with absolute certainty, given enough information. Before Heisenberg's work, the prevailing view in physics was shaped by classical mechanics, where scientists like Isaac Newton had proposed that if all the forces acting on an object were known, its future behavior could be precisely determined. Classical physics painted a deterministic picture of the universe, where the past and future of every object could be traced through exact knowledge of its position, velocity, and the forces acting upon it. This worldview was rooted in the idea that if one had sufficient knowledge about a system, they could predict its behavior with unwavering accuracy. However, Heisenberg's discovery revolutionized this thinking by revealing that, at the quantum level, certainty could no longer be claimed in the same way. Heisenberg's uncertainty principle arose from the complexities of quantum mechanics, which describes the behavior of particles on the smallest scales, such as electrons, protons, and other subatomic particles. In the quantum world, the very act of measuring certain properties, like the position or momentum of a particle, introduces an inherent uncertainty in the measurement of the complementary property. Heisenberg's uncertainty principle is most commonly expressed through a mathematical equation that relates the uncertainties in position, deltax, and momentum, deltap, of a particle. Deltax times deltap is greater than or equal to H 2 inches. This equation. Deltax represents the uncertainty in position, deltap represents the uncertainty in momentum, and H is the reduced Planck's constant, which is a fundamental constant in quantum mechanics. The equation captures the relationship between the uncertainties in the measurements of position and momentum. The principle essentially states that the more precisely one measures the position of a particle, the less precisely one can know its momentum, and vice versa. The product of these uncertainties will always be greater than or equal to half the value of Planck's constant. This is not a limitation of the measurement tools used, but rather a fundamental property of nature itself, arising from the wave-particle duality of quantum objects. The core insight of the uncertainty principle is that particles do not have definite, fixed values for both position and momentum at the same time. Unlike classical objects, which can be described by both their precise location and speed, quantum objects exist in a state of probability. Instead of having definite properties, particles are described by a probability distribution, meaning they are spread out over a range of possible locations and momenta. When a measurement is made, the particle collapses into a specific value for that property, but this collapse is governed by probabilities, not certainties. This revelation was at odds with classical physics, where objects like planets or everyday items were believed to have well-defined positions and velocities at all times. The fact that quantum particles do not possess these definite properties unless measured was a fundamental shift in how scientists had to approach the behavior of matter on the smallest scales. Heisenberg's uncertainty principle highlighted the inherent indeterminacy in quantum systems, and it forced physicists to reconsider their entire understanding of reality itself. It was no longer possible to think of the universe as a precise machine where everything could be predicted based on initial conditions. Instead, it became clear that the quantum world was probabilistic, where predictions could only be made in terms of likelihoods. In essence, Heisenberg's Uncertainty Principle forces us to acknowledge the limits of human knowledge. The precision of our measurements in the quantum world is fundamentally limited. The principle directly contradicts the deterministic worldview that dominated classical mechanics, where every event was seen as an outcome of preceding events. The uncertainty principle introduced the concept of probability, where scientists could no longer make predictions with complete certainty. Instead, they could only make probabilistic statements about the future behavior of quantum particles. The uncertainty principle also raised profound questions about the nature of observation and reality. In classical physics, an observer could measure the properties of a system without fundamentally altering the system itself. However, in the quantum realm, the act of measurement itself changes the system being observed. This is often referred to as the observer effect, where the very process of measuring a quantum system influences its state. For example, when trying to measure the position of an electron, the act of measuring it might change its momentum, and vice versa. This means that the observer is not a passive entity, but an active participant in shaping the outcome of a measurement. The observer effect challenges our traditional notions of objectivity and suggests that reality may be more intertwined with observation than previously thought. Moreover, Heisenberg's principle helped establish the foundation for the probabilistic interpretation of quantum mechanics, which was later developed by physicists like Niels Bohr and Erwin Schrödinger. The wave function, a key concept in quantum mechanics, describes the probability distribution of a particle's position or momentum. According to this interpretation, before a measurement is made, a quantum particle exists in a superposition of states, and it only chooses a particular state when measured. This idea is embodied in Schrödinger's famous thought experiment with his cat, where a cat is considered to be both alive and dead until observed. The uncertainty of quantum particles is mirrored in the uncertainty of the cat's fate, reflecting the indeterminacy inherent in the quantum world. The implications of Heisenberg's uncertainty principle extend far beyond theoretical discussions. They have practical consequences in the field of quantum technology. One of the most significant applications of quantum mechanics in the modern world is quantum computing. Quantum computers harness the principles of superposition and entanglement to perform computations in ways that classical computers cannot. However, these technologies also rely on managing the uncertainties and probabilistic nature of quantum systems. The uncertainty principle, while posing challenges to precise control over quantum systems, also provides opportunities to exploit these uncertainties for powerful new technologies. Researchers are working to develop quantum algorithms that can take advantage of these unpredictable behaviors to solve complex problems more efficiently than classical computers. Furthermore, Heisenberg's principle has had an enduring impact on the philosophy of science. It has raised important questions about the limits of human knowledge and the role of observation in the construction of reality. Before Heisenberg, many scientists believed that with enough knowledge and the right tools, humans could ultimately know everything about the universe. But the uncertainty principle introduces a fundamental limit to this aspiration. It suggests that, at least in the quantum realm, there are inherent limits to what we can know, and these limits are built into the fabric of the universe itself. In conclusion, Heisenberg's uncertainty principle represents a dramatic departure from the classical worldview. It has forced us to rethink not only how we understand the behavior of particles, but also how we think about the nature of knowledge, observation, and reality. Quantum mechanics, with all its uncertainty and indeterminacy, provides a more nuanced and complex view of the universe, one in which probabilities replace certainties, and the act of measurement itself plays a crucial role in shaping the outcome. Heisenberg's legacy is profound, as it has shaped our understanding of the quantum world and laid the groundwork for the development of technologies that will continue to transform our world for generations to come. His work challenges us to accept the limits of human knowledge and invites us to explore the mysteries of a universe that, at its most fundamental level, may be far more uncertain than we had ever imagined. The legacy of Werner Heisenberg's uncertainty principle continues to shape the very foundation of modern physics and our understanding of the quantum realm. After its introduction in 1927, it has not only revolutionized physics, but also reshaped our philosophical approach to reality, knowledge, and observation. To delve deeper into the profound implications of the uncertainty principle, we must explore its far-reaching effects on the philosophy of science, its practical applications in quantum technologies, and its ongoing influence in the fields of physics and beyond. At its core, the uncertainty principle invites us to reconsider the traditional notion of determinism that dominated classical physics. In classical mechanics, the universe was seen as a vast, interconnected system governed by fixed laws of motion. If one knew the positions and velocities of all particles at any given time, the future of the system could be predicted with perfect accuracy. This deterministic view, epitomized by figures like Isaac Newton, suggested that the universe operated like a giant clockwork mechanism, where every event followed from preceding conditions. However, Heisenberg's principle dispelled this notion by introducing inherent unpredictability at the quantum level. This probabilistic nature of quantum mechanics had profound implications for how we understand the behavior of particles. In the quantum realm, objects such as electrons do not have fixed, measurable values for both position and momentum at the same time. Instead, they exist in a state of probability, represented by a wave function. This wave function provides the likelihood of finding a particle in a particular location or having a specific momentum, but it never gives us absolute certainty. This was a drastic departure from classical physics, where such properties could be determined with precision. The uncertainty principle thus introduced the idea that the sparked universe, at the smallest scales, is inherently probabilistic and that certainty is unattainable. One of the most fascinating aspects of Heisenberg's uncertainty principle is its implications for the act of measurement. In classical physics, measurements were thought to be a passive observation of the world. You could measure the properties of a system without affecting it, but quantum mechanics, as highlighted by the uncertainty principle, suggests that the very act of measurement alters the system being measured. This is particularly evident in the behavior of particles such as electrons, which can be influenced by the act of observation. When trying to measure the position of an electron, for example, the momentum of the particle becomes less well-defined, and vice versa. This concept challenges the idea of an objective, detached observer and brings the observer into the very fabric of the measurement process. The role of the observer in quantum mechanics has led to philosophical debates about the nature of reality itself. If observation affects the state of a system, then what does this mean for our understanding of the universe when it is not being observed? This is the essence of what is often referred to as the measurement problem in quantum mechanics. The uncertainty principle raises the possibility that, at least on a microscopic scale, the universe may not have well-defined properties until it is measured or observed. This challenges the classical notion that the world exists independently of our perception of it. Instead, quantum mechanics suggests that the act of observing or measuring is intimately tied to the very existence of the properties being observed. In this sense, the observer becomes an active participant in the creation of reality, not just a passive bystander. The uncertainty principle has had a profound influence on the development of quantum mechanics, particularly in the interpretation of quantum phenomena. One of the most notable Contributions to this understanding came from Niels Bohr and his complementarity principle, which suggested that different experimental setups reveal different aspects of a system, and both aspects are necessary to understand the full picture of reality. Bohr and Heisenberg, along with other physicists, developed a new interpretation of quantum mechanics in which the particle-like and wave-like behavior of quantum objects were understood to be complementary. The uncertainty principle helped solidify this view, as it was clear that it was not possible to simultaneously measure both aspects with precision. Beyond its theoretical significance, Heisenberg's uncertainty principle has had a lasting impact on practical fields, particularly in the development of quantum technologies. One of the most exciting areas where quantum mechanics and the uncertainty principle have come to fruition is in the field of quantum computing. Quantum computers, unlike classical computers, exploit the principles of superposition and entanglement to perform computations that would be impossible for classical machines. Quantum bits or qubits can exist in multiple states simultaneously, allowing quantum computers to solve certain problems exponentially faster than their classical counterparts. However, these qubits are also subject to the uncertainty principle, which introduces a level of unpredictability and noise into quantum calculations. Managing these uncertainties is a major challenge in building reliable quantum computers, but it also opens up new possibilities for encryption and computational power. Another area where the uncertainty principle plays a crucial role is in quantum cryptography, which uses the principles of quantum mechanics to create ultra-secure communication systems. Quantum key distribution, QKD, for instance, uses quantum states to generate cryptographic keys that are practically immune to interception. The act of measuring a quantum state, as dictated by the uncertainty principle, alters the state of the system, making eavesdropping on quantum communication detectable. This feature of quantum mechanics ensures that any attempt to intercept a quantum message will disrupt the system, alerting the sender and receiver to the intrusion. Quantum cryptography, thus, represents a practical application of the uncertainty principle, turning a fundamental limitation into an asset for security. The uncertainty principle's influence extends beyond physics and technology. It has also shaped the way we think about knowledge and the limitations of human understanding. In classical science, there was a belief that with the right tools, we could ultimately know everything about the universe. However, Heisenberg's principle forced scientists to acknowledge that there are inherent limits to what can be known, and these limits are intrinsic to the nature of reality. This realization led to a shift in how we view scientific inquiry. Instead of seeking absolute certainty, scientists now recognize the value of probability and approximation. The uncertainty principle suggests that there will always be aspects of the universe that elude precise measurement, and that uncertainty is not something to be eliminated, but something to be embraced and understood. In philosophy, Heisenberg's uncertainty principle has raised important questions about the relationship between perception, knowledge, and reality. Philosophers have long debated the nature of reality and whether it exists independently of our perception of it. The uncertainty principle seems to suggest that, at least in the quantum world, reality does not have well-defined properties until it is measured. This idea has led to various philosophical interpretations, such as the Copenhagen interpretation, which asserts that quantum systems exist in a superposition of states until they are observed. Other interpretations, such as the many worlds hypothesis, propose that every possible outcome of a quantum event actually occurs, each in a separate branch of reality. Heisenberg's uncertainty principle, while challenging our understanding of the universe, has also provided new avenues for exploring the very nature of existence. It has forced physicists and philosophers alike to grapple with the limits of knowledge and to confront the mysterious and unpredictable nature of the quantum world. As technology continues to advance, and quantum systems are harnessed for practical applications, the legacy of the uncertainty principle will only continue to grow, reshaping our understanding of reality and our place within it. In conclusion, Heisenberg's uncertainty principle is not just a theoretical construct, it is a fundamental insight into the nature of the universe. It challenges classical notions of determinism, alters our understanding of measurement and observation, and has paved the way for groundbreaking advancements in quantum technology. While it highlights the inherent uncertainties of the quantum world, it also offers a deeper understanding of the probabilistic nature of reality. Heisenberg's legacy continues to influence the course of modern physics and serves as a reminder that uncertainty, far from being a weakness, is an integral part of the universe's fabric. Heisenberg's uncertainty principle, introduced in 1927, marks one of the most profound shifts in the history of physics. The second keynote of our discussion delves into the implications of this principle, the understanding of quantum mechanics as a probabilistic world of possibilities. This insight has completely transformed how we think about the microscopic world, where particles such as electrons and photons behave in ways that defy our classical expectations. The uncertainty principle, more than just a limitation on measurements, opened the door to an entirely new way of thinking about the behavior of nature at its most fundamental level. To grasp the full significance of this insight, we must first understand the difference between classical physics and quantum mechanics. Classical physics, epitomized by Newtonian mechanics, describes the motion of objects in a deterministic way. According to classical physics, if one knows the position and velocity of an object at any given time, one can predict its future motion with absolute certainty. This concept of determinism is rooted in the belief that the universe operates like a clockwork mechanism, with every event following from the one before it. The only challenge in classical mechanics was gathering the necessary information to make predictions. With sufficient data, every outcome could be predicted with pinpoint accuracy. However, the advent of quantum mechanics revealed a radically different picture. Quantum mechanics describes the behavior of particles at the atomic and subatomic levels. At this scale, particles such as electrons do not behave like tiny billiard balls with definite positions and velocities that can be tracked over time. Instead, they exhibit wave-particle duality, meaning they can behave like both particles and waves, depending on the experiment. This duality led to a profound realization: particles do not have fixed, precise properties unless measured. Before measurement, the properties of quantum objects, such as their position or momentum, are described by a probability distribution. This probability distribution reflects the likelihood of finding a particle in a particular location or with a certain momentum, but it does not provide absolute certainty. This probabilistic nature of quantum mechanics was a departure from classical physics and fundamentally challenged the deterministic worldview that had been established over centuries. The concept that particles exist in multiple states simultaneously, in what is known as a superposition, was alien to classical thinking. Heisenberg's uncertainty principle was the key to understanding this new reality. It states that there is a limit to how precisely we can know both the position and momentum of a particle at the same time. This limitation is not due to the imperfections in our measuring tools, but is inherent in the nature of quantum objects. The more precisely we measure one of these properties, the less precisely we can know the other. The mathematical formulation of the uncertainty principle, expressed as deltax times deltap, is greater than or equal to HOD2, reveals the relationship between the uncertainties in position, deltax, and momentum, deltap, of a particle. Here, H represents the reduced Planck constant, a fundamental constant in quantum mechanics. This equation implies that there is an inverse relationship between the precision with which we can measure position and momentum. The uncertainty in one property increases as the uncertainty in the other decreases. The uncertainty principle is not just a theoretical construct, but an intrinsic feature of quantum systems. It is a manifestation of the wave-like nature of particles and the way in which they interact with the measuring apparatus. One of the key consequences of the uncertainty principle is that particles do not have definite values for their properties until they are observed. Before measurement, their properties are not just unknown, they are undefined. For example, an electron does not have a precise position until we measure it. Instead, it exists in a range of possible locations, spread out according to a probability wave. This idea is embodied in the wave function, a mathematical description of the quantum state of a particle. The wave function provides the probability distribution for the particle's position, momentum, and other properties. Only when we measure the position, for example, does the wave function collapse and the particle assumes a definite position. Before measurement, however, the particle exists in a superposition of states where it can be in multiple positions or have multiple momenta at once. This probabilistic nature is profoundly different from the deterministic worldview of classical physics. In classical physics, we can, in principle, track an object's motion with complete precision and predict its future trajectory. In quantum mechanics, the act of measurement introduces an element of uncertainty, and predictions can only be made in terms of probabilities. Instead of being able to track the path of an electron with certainty, we can only say where the electron is likely to be found based on a probability distribution. This new way of thinking about nature was a direct result of Heisenberg's insight into the limits of measurement, and it laid the foundation for the probabilistic interpretation of quantum mechanics. In practical terms, the uncertainty principle has far-reaching consequences for how scientists approach the behavior of particles at the quantum level. It means that we cannot know everything about a quantum system at once. This limitation fundamentally changes how we think about measurement in the quantum world. The more precisely we try to measure one aspect of a particle, the more uncertain we become about the other. This is evident in experiments such as the double-slit experiment, where particles like electrons create interference patterns, behaving like waves when they are not observed, but act like particles when they are measured. The act of observation itself changes the behavior of the system, a feature that is unique to quantum systems and a direct consequence of Heisenberg's uncertainty principle. Moreover, this uncertainty is not limited to just position and momentum. It applies to other pairs of complementary properties, such as energy and time. For example, the uncertainty in the energy of a system and the time during which the energy is measured are related by a similar principle. This idea has profound implications for the stability and behavior of quantum systems. It suggests that there is an inherent fuzziness in the energy levels of particles, and this fuzziness has practical consequences in phenomena such as spontaneous emission and the behavior of atoms in excited states. In addition to its theoretical implications, Heisenberg's uncertainty principle also plays a significant role in the development of quantum technologies. Quantum computing, for instance, leverages the principles of quantum mechanics to perform computations that would be infeasible for classical computers. In quantum computing, qubits can exist in superposition states, allowing them to represent multiple values simultaneously. However, the uncertainty in the measurement of qubits is a crucial factor that researchers must consider when developing reliable quantum computers. Despite these uncertainties, quantum computing holds great promise for solving problems that are currently beyond the reach of classical computers, such as factoring large numbers and simulating complex quantum systems. Quantum cryptography, another field influenced by the uncertainty principle uses the inherent uncertainty of quantum measurements to create secure communication channels. In quantum key distribution, QKD, the security of the communication relies on the fact that any attempt to eavesdrop on the communication will introduce detectable disturbances due to the uncertainty principle. When quantum bits, qubits, are measured, their state is altered, and any attempt to intercept the communication will be noticed. This makes quantum cryptography a powerful tool for secure communication, especially in fields where privacy and security are paramount. Despite the many advances in quantum technology, the uncertainty principle also highlights the limitations of human knowledge. It suggests that there are aspects of reality that are fundamentally unknowable and that our understanding of the universe is inherently limited. This limitation has profound philosophical implications, particularly when it comes to our understanding of the nature of reality. In classical physics, it was believed that with enough data and the right tools, we could ultimately know everything about the universe. But Heisenberg's uncertainty principle reminds us that there are limits to what we can know, and these limits are an intrinsic part of the quantum world. This idea has led to a shift in how scientists and philosophers think about knowledge, reality, and the role of observation in shaping the world around us. In conclusion, the uncertainty principle, introduced by Heisenberg, is not just a statement about the limitations of measurement tools. It is a fundamental insight into the nature of reality at the quantum level. It challenges the deterministic worldview of classical physics and reveals a probabilistic universe where particles exist in states of uncertainty until they are measured. This insight has reshaped our understanding of the quantum world and has had far-reaching implications in both theoretical physics and practical applications. From quantum computing to quantum cryptography, the uncertainty principle continues to guide research and technological development, while also challenging our fundamental assumptions about the nature of knowledge and reality itself. As we continue to explore the mysteries of the quantum world, Heisenberg's legacy will remain a cornerstone of our understanding of the universe at its most fundamental level. Heisenberg's uncertainty principle focuses on a significant transformation in the way scientists perceive and model the physical world at the quantum level, quantum mechanics as a world of probabilities. This shift, driven by the uncertainty principle, challenges the classical understanding of determinism and instead introduces an inherently probabilistic model of nature. The implications of this transformation are far-reaching, affecting not just the foundations of physics, but also the way we think about measurement, reality, and our understanding of the universe itself. To understand the true depth of Heisenberg's contribution, we need to contrast it with the classical worldview that governed physics for centuries. Classical physics, particularly as formulated by Isaac Newton, is deterministic. This means that if we know the position, velocity, and forces acting on an object at any given time, we can predict its future state with complete certainty. This vision of the universe as a vast, interconnected system of predictable events, much like a mechanical clockwork, was the dominant framework in science. It painted a picture of the universe as orderly and predictable, with every cause leading directly to an effect. As a result, physicists believed that, with enough information, the future of any system could be predicted with absolute accuracy. Quantum mechanics, and particularly Heisenberg's uncertainty principle, shattered this classical view. Heisenberg's principle introduced the idea that at the quantum level, particles such as electrons and photons do not have well-defined positions and momenta at the same time. The uncertainty principle asserts that there is an inherent limit to how precisely we can measure the position and momentum of a particle simultaneously. More precisely, the act of measuring one of these properties disturbs the other, introducing a fundamental uncertainty into any attempt to precisely define both. This was not due to limitations in our measurement tools, but was an intrinsic feature of nature itself. The more accurately we measure the position of a particle, the more uncertain its momentum becomes, and vice versa. This probabilistic nature is a stark departure from the certainty and precision championed by classical physics. The central concept that emerged from Heisenberg's uncertainty principle is that quantum systems are not governed by certainty, but by probability. In classical physics, we could track an object's position and velocity with great precision, but in the quantum world, particles are described not by definite properties, but by a wave function that gives the probability of finding a particle in a particular position or with a particular momentum. This wave function, a mathematical description of a particle's quantum state, reflects the superposition of all possible states the particle could be in before a measurement is made. Upon measurement, the wave function collapses and the particle assumes a definite state, but only at that moment. Until the measurement occurs, the particle's properties exist in a cloud of probabilities, not certainties. This understanding of particles existing in a superposition of states where they can be in multiple positions or have multiple momenta simultaneously was a revolutionary idea. It directly contradicted the classical view of particles as having precise and definite attributes. Instead, quantum mechanics introduced the notion that, at the fundamental level, the behavior of particles is not deterministic but probabilistic. The wave function does not tell us exactly where a particle is or how fast it is moving. It only provides the likelihood of where the particle might be found and with what momentum when measured. In essence, quantum mechanics deals in probabilities, not certainties. The implications of this probabilistic worldview are profound. The uncertainty principle forces us to rethink not only how we measure quantum systems, but also how we understand the very nature of those systems. In classical physics, we could imagine that an object's properties such as position and momentum existed independently of whether we measured them. But in quantum mechanics, the properties of a particle are not fully determined until they are measured. This brings into question the role of the observer. If measurement can alter the state of a system, then how can we trust our observations of the quantum world? In this sense, the observer becomes an active participant in the process of measurement, shaping the outcome of the system. The act of observing a particle changes its state, and as a result, we cannot talk about the properties of a quantum system without considering the measurement itself. This shift from a deterministic to a probabilistic framework in quantum mechanics is perhaps best illustrated by the famous thought experiment known as Schrödinger's cat. In this thought experiment, a cat is placed inside a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the Geiger counter detects radiation from the decaying atom, it triggers the release of poison, killing the cat. If the atom does not decay, the cat remains alive. According to classical physics, the cat is either alive or dead, but in quantum mechanics, until the box is opened and the cat is observed, the cat is in a superposition of states, both alive and dead at the same time. This paradox underscores the strange and counterintuitive nature of quantum mechanics, where the state of a system is not defined until it is observed. The probabilistic nature of quantum mechanics also leads to a concept known as quantum indeterminacy, which suggests that the universe at the quantum level is inherently unpredictable. Unlike classical mechanics, where, given the initial conditions of a system, one can calculate its future evolution with certainty, quantum mechanics only allows us to calculate the probability of certain outcomes. This realization has profound philosophical implications. If the fundamental building blocks of nature are governed by probabilities rather than certainties, then the universe, at least at the quantum level, is fundamentally indeterministic. This idea challenges our classical notion of causality and forces us to confront the limits of human knowledge. Moreover, the introduction of probabilities into our understanding of the physical world has significant consequences for our interpretation of the nature of reality itself. In classical physics, it was assumed that the universe exists independently of our observations, and that the properties of objects are well defined regardless of whether or not they are being observed. But in quantum mechanics, the act of measurement plays a critical role in determining the state of the system. The question arises, does the universe exist in a definite state when we are not observing it? Or is it only when we measure the system that it collapses into a specific state? This question lies at the heart of what is often referred to as the measurement problem in quantum mechanics. The probabilistic interpretation of quantum mechanics is not limited to abstract theoretical concepts, but also has practical applications. In fact, the uncertainty principle and the probabilistic nature of quantum mechanics have led to the development of quantum technologies that are beginning to shape the future of science and engineering. Quantum computers, for example, exploit the principles of superposition and entanglement to perform calculations that would be impossible for classical computers. In quantum computing, qubits, quantum bits, can exist in multiple states simultaneously, allowing them to process vast amounts of data in parallel. However, the uncertainty and probabilistic nature of qubits present significant challenges in controlling and measuring quantum systems. Managing the uncertainties inherent in quantum systems is one of the key obstacles in building practical quantum computers, but it is also what makes quantum computing so powerful. Similarly, quantum cryptography, which leverages the principles of quantum mechanics to create secure communication channels, relies on the uncertainty principle to ensure the privacy of transmitted information. In quantum key distribution, QKD, any attempt to intercept the transmission alters the quantum state of the system, making eavesdropping detectable. This is because the act of measurement in quantum systems disturbs the state of the system, which can be detected by the sender and receiver. Quantum cryptography, therefore, offers a level of security that is not possible with classical encryption methods. In conclusion, Heisenberg's uncertainty principle has far-reaching consequences for both the theory and practice of physics. It forces us to abandon the classical deterministic worldview and embrace a probabilistic model of nature where particles do not have definite properties until measured. This realization challenges not only our understanding of the physical world, but also our philosophical notions of reality, observation, and knowledge. Quantum mechanics, guided by Heisenberg's uncertainty principle, has reshaped our view of the universe, revealing a world that is inherently unpredictable and uncertain. Despite the challenges posed by this uncertainty, quantum technologies are emerging as powerful tools that leverage these very principles to revolutionize fields such as computing and cryptography. Heisenberg's legacy continues to shape our understanding of the quantum world, guiding us into new realms of scientific exploration and technological innovation. The uncertainty principle, first introduced by Werner Heisenberg in 1927, represents one of the most pivotal and challenging concepts in the history of physics. It not only reshaped our understanding of the microscopic world, but also helped establish quantum mechanics as a radically different paradigm from classical physics. The third keynote in our exploration of Heisenberg's legacy delves into the mathematical foundation of the uncertainty principle and the way it directly challenges our preconceived notions of precision, determinism, and measurement in the natural world. The core idea behind the uncertainty principle is that certain pairs of physical properties, like position and momentum, cannot be simultaneously known with perfect accuracy. This principle is mathematically expressed by the equation deltax times deltap is greater than or equal to h2, where deltax represents the uncertainty in the position of a particle, deltap represents the uncertainty in its momentum, and HA is the reduced Planck's constant. This equation tells us that there is an inherent limit to the precision with which we can measure both the position and momentum of a particle at the same time. The more precisely we try to measure one of these quantities, the less precise our measurement of the other becomes. This fundamental limitation is not due to imperfections in our measurement instruments, but is an intrinsic property of quantum systems. It is a result of the wave-particle duality of particles and the uncertainty that arises from their quantum nature. Heisenberg's uncertainty principle forces us to abandon the classical notion that the universe operates in a deterministic manner, where all aspects of a system can be known and predicted precisely. In classical physics, determinism is the idea that, given enough information about the initial conditions of a system, one could predict its future state with perfect accuracy. For instance, if we know the position and velocity of a car at a given moment, we can predict its future motion based on Newton's laws of motion. Classical physics paints a picture of the universe as a giant machine, where every event follows a predictable chain of causes and effects. However, the quantum world, as revealed by Heisenberg, does not operate in such a deterministic manner. Instead, the properties of quantum objects, like electrons, are not well defined until they are measured, and even then, they can only be described in terms of probabilities, not certainties. This probabilistic nature is rooted in the fact that particles at the quantum level, such as electrons, do not have definite positions and momenta in the classical sense. Instead, they exist as wave functions, which are mathematical descriptions of the probability distribution of a particle's properties. Before measurement, a quantum object, like an electron, is not located at a specific position, but exists as a cloud of probabilities, with different locations having different likelihoods. When a measurement is made, the wave function collapses, and the particle assumes a definite position. However, the act of measurement disturbs the system, and the exact momentum of the particle is no longer precisely known. This wave-particle duality, where particles behave both as waves and as particles, is a cornerstone of quantum mechanics and a direct consequence of Heisenberg's uncertainty principle. The mathematical equation that expresses the uncertainty principle also encapsulates the very nature of quantum systems. The reduced Planck constant is an incredibly small number, reflecting the scale at which quantum effects become significant. Planck's constant, h, is a fundamental constant in quantum mechanics that represents the smallest possible unit of action in the quantum world. This reduced Planck constant, ha, is essentially Planck's constant divided by 2 pi, and it plays a central role in the quantization of energy levels and the uncertainty in measurements. This smallness of Planck's constant is one of the reasons why the uncertainty principle has a negligible effect on macroscopic objects where quantum effects are not observable. However, at the microscopic level, such as with atoms and subatomic particles, the uncertainty becomes pronounced and inescapable. The uncertainty principle can also be understood in terms of the wave-particle duality of quantum objects. According to wave-particle duality, particles such as electrons exhibit both particle-like and wave-like behavior, depending on the experiment being conducted. When we attempt to measure the position of a particle, we are localizing it to a specific point in space, and in doing so, we are interacting with the particle as though it were a localized point object. However, in the wave-like regime, the gripped particle is described by a wave function that spreads out over a range of possible locations. This dual nature of particles introduces a fundamental tension between the precision with which we can measure the position and momentum of a particle. The more precisely we measure the position of a particle, the less precise our knowledge of its momentum becomes, because the particle's wave function spreads out in momentum space as it is confined in position space. To grasp the full significance of the uncertainty principle, it is important to recognize that it is not just about the limitations of measurement, but reflects a deeper, intrinsic property of nature. Heisenberg's uncertainty principle is a direct consequence of the quantum nature of the universe. It arises because particles, unlike macroscopic objects, do not have definite positions and velocities in the same sense that classical objects do. The uncertainty principle is not an artifact of our measuring tools or a technical limitation. It is a feature of the quantum world itself. In fact, it highlights the non-deterministic and probabilistic nature of quantum systems, where particles exist in a state of potentiality until they are observed. In the context of quantum mechanics, this uncertainty is fundamental to the behavior of particles. Unlike in classical mechanics, where objects have well-defined positions and momenta that evolve smoothly over time, quantum systems are described by a wave function that encapsulates the probabilities of all possible states of the system. When a measurement is made, the wave function collapses, and the particle assumes a specific state, but until that point, its properties are uncertain and described only probabilistically. This uncertainty is a natural consequence of the principles of quantum mechanics and is inherent to the very fabric of the universe. The uncertainty principle has had profound implications for our understanding of the world around us. It challenges the classical worldview and forces us to rethink our notions of knowledge, determinism, and observation. If we are to truly understand the quantum world, we must accept that uncertainty is not just an inconvenience to be overcome. It is a fundamental feature of nature that governs the behavior of particles. In this sense, Heisenberg's uncertainty principle is a reminder that our knowledge of the world is always limited, and that the act of observation itself plays a crucial role in shaping the reality we observe. In the broader context of quantum mechanics, the uncertainty principle also played a key role in the development of quantum theory and its interpretation. The principle suggests that we can never know both the position and momentum of a particle with absolute precision, leading to a probabilistic interpretation of the quantum world. This interpretation, known as the Copenhagen interpretation, asserts that particles do not have definite properties until they are measured and that their behavior is governed by probabilities rather than certainties. Other interpretations of quantum mechanics, such as the many-worlds hypothesis, also incorporate the uncertainty principle and challenge our classical understanding of reality. In practical terms, the uncertainty principle has had significant implications for the development of modern technologies, particularly in the field of quantum computing. Quantum computers, unlike classical computers, use qubits, quantum bits, that can exist in multiple states simultaneously, thanks to the principles of superposition and entanglement. These quantum systems rely on the probabilistic nature of quantum mechanics to perform calculations that would be infeasible for classical computers. However, the uncertainty principle also imposes challenges for quantum computing, as the measurement of quantum states introduces uncertainty into the system. Despite these challenges, quantum computing holds enormous potential for solving complex problems in fields such as cryptography, artificial intelligence, and optimization. In addition to quantum computing, the uncertainty principle has found practical applications in quantum cryptography, where it is used to create secure communication channels. In quantum key distribution, QKD, for example, the uncertainty principle ensures that any attempt to intercept the communication will disturb the quantum states of the system, making eavesdropping detectable. This principle provides a level of security that is impossible to achieve with classical cryptographic methods, and it is already being used to develop ultra-secure communication systems. The uncertainty principle, while initially met with skepticism, has become one of the central tenets of modern physics. It has profoundly impacted the way scientists think about the nature of reality, measurement, and knowledge. It has also spurred the development of new technologies that rely on the strange and counterintuitive properties of the quantum world. The uncertainty principle is a testament to the fact that, in the quantum realm, uncertainty is not merely a limitation, but a fundamental feature of the universe. It is a principle that continues to inspire new discoveries and challenges our deepest assumptions about the nature of reality. In conclusion, Heisenberg's uncertainty principle has reshaped the landscape of physics and our understanding of the universe. It challenges the deterministic worldview of classical mechanics and introduces a probabilistic model of nature that governs the behavior of quantum systems. The principle reveals that particles do not have precise properties until measured, and that uncertainty is an inherent feature of quantum mechanics. This fundamental insight has profound implications for both the theory and practice of physics, and continues to influence the development of new technologies, such as quantum computing and quantum cryptography. Heisenberg's uncertainty principle is a reminder that the universe at its most fundamental level is unpredictable, and that uncertainty is a core aspect of the quantum world. Heisenberg's uncertainty principle has left an indelible mark on both theoretical physics and our understanding of the natural world. The third keynote explores how this principle not only altered the theoretical landscape of physics, but also challenged fundamental notions of knowledge, observation, and the nature of reality itself. In its simplest form, the uncertainty principle tells us that certain pairs of physical properties, such as position and momentum, cannot be measured simultaneously with absolute precision. This limitation isn't due to any flaw in our measurement devices, but instead is an inherent feature of quantum systems. The principle forces us to reconsider what it means to know something in the world of quantum mechanics, and how measurements play an active role in shaping the very systems we seek to understand. To truly appreciate the depth of Heisenberg's uncertainty principle, it's essential to first look at how classical mechanics shaped our understanding of the world and how the uncertainty principle fundamentally disrupted this framework. Classical physics, which dominated our understanding of the physical world for centuries, is rooted in the idea of determinism. In classical mechanics, introduced by Isaac Newton, the motion of objects could be predicted with absolute certainty, as long as we had sufficient knowledge of their positions and velocities at any given time. This worldview suggested that the universe was a vast machine, operating with precision and predictability, where every cause had an effect and every event followed from its preceding cause. The future could be determined from the past if we could track the forces acting on an object and the state it was in. We could predict its behavior with perfect accuracy. However, the emergence of quantum mechanics in the early 20th century revealed that the microscopic world of atoms, subatomic particles, and photons did not conform to the neat, predictable laws of classical physics. Instead, the behavior of particles at this scale is inherently probabilistic, and Heisenberg's uncertainty principle was the first formal recognition of this fundamental shift. The principle tells us that at the quantum level, there are limits to how precisely we can know the properties of particles. For example, if we measure the position of a particle with high precision, the uncertainty in its momentum will increase, and vice versa. This is encapsulated in the mathematical relationship deltax times deltap is greater than or equal to 2, where deltax is the uncertainty in position, deltap is the uncertainty in momentum, and ha is the reduced Planck constant. The uncertainty principle challenges the classical notion that the universe operates in a deterministic fashion, where the future state of a system is fully determined by its current state. Instead, Heisenberg's insight introduces the concept of probabilistic outcomes, where the position and momentum of quantum particles can only be described in terms of likelihoods, not certainties. This realization has profound implications for the way we understand not only the behavior of particles but also the limits of human knowledge and measurement. It forces us to accept that at the quantum level, uncertainty is a fundamental aspect of reality, not a limitation of our tools. The uncertainty principle is also intrinsically connected to the wave-particle duality of quantum objects. Classical physics viewed particles and waves as distinct entities, with particles having fixed positions and velocities, and waves propagating through space without a fixed location. However, quantum mechanics revealed that particles, like electrons, exhibit both particle-like and wave-like behavior, depending on the experimental setup. When trying to measure a particle's position with high precision, we are forced to treat it as a localized point object. Yet, when we try to measure its momentum, we must treat it as a wave. The wave-like nature of particles introduces uncertainty into our ability to measure both position and momentum with absolute precision, as the very act of measurement changes the state of the system. The uncertainty principle thus reflects the wave-particle duality of quantum objects, highlighting the fact that the more we try to localize a particle in one domain, position, the more uncertain it becomes in the complementary domain, momentum. To further understand the significance of Heisenberg's uncertainty principle, we need to explore the fundamental difference between classical and quantum systems. In classical physics, objects are considered to have well-defined properties at all times, regardless of whether they are being observed. If we know an object's position and velocity, we can calculate its future trajectory with precision. Quantum mechanics, on the other hand, tells us that particles do not have well-defined properties until they are measured. Instead, they exist in a superposition of all possible states, and only upon measurement do they collapse into a definite state. This inherent uncertainty is not due to external factors like imprecise instruments. It is a fundamental property of quantum systems themselves. This shift from determinism to probabilism is one of the most radical aspects of quantum mechanics and has far-reaching implications for both the theory and practice of physics. The uncertainty principle not only reveals the limitations of our measurement tools but also forces us to reconsider the very nature of knowledge itself. In the quantum world, the concept of knowledge is inherently probabilistic. We can never know both the position and momentum of a particle with perfect precision at the same time. Instead, we work with probabilities, making predictions about where a particle might be found or with what momentum it might be moving. This probabilistic approach has led to the development of quantum mechanics as a theory that provides only statistical descriptions of the behavior of particles rather than deterministic ones. One of the profound philosophical implications of the uncertainty principle is its challenge to the classical idea of an objective reality that exists independently of observation. In classical physics, an object's properties, whether it is at a particular location or moving at a certain speed, are considered to exist objectively, whether or not anyone is observing them. But in quantum mechanics, the act of observation itself plays a critical role in determining the properties of a system. The famous thought experiment, known as Schrödinger's cat, illustrates this concept. According to the Copenhagen interpretation of quantum mechanics, the cat inside the box is both alive and dead at the same time, existing in a superposition of states until the box is opened, and the cat is observed. In this view, the act of observation collapses the superposition into a definite state. The uncertainty principle thus highlights the active role of the observer in determining the state of a quantum system and challenges the classical notion that the universe exists independently of our observation of it. In terms of practical applications, the uncertainty principle has had a significant impact on the development of quantum technologies, which exploit the strange properties of quantum systems. One of the most promising applications of quantum mechanics is in the field of quantum computing. Quantum computers use quantum bits, or qubits, which can exist in a superposition of states, allowing them to perform certain types of calculations much faster than classical computers. However, qubits are also subject to the uncertainty principle, and managing the uncertainties inherent in quantum systems is one of the key challenges in building reliable quantum computers. Despite these challenges, quantum computing has the potential to revolutionize fields such as cryptography, artificial intelligence, and optimization. Another area where the uncertainty principle has practical implications is in quantum cryptography. Quantum key distribution, QKD, uses the principles of quantum mechanics to create secure communication channels. In QKD, the uncertainty principle ensures that any attempt to eavesdrop on the communication will disturb the quantum states of the system, making eavesdropping detectable. This creates a level of security that is not possible with classical encryption methods, as the very act of measuring quantum states alerts the sender and receiver to any potential interception. In conclusion, Heisenberg's uncertainty principle is one of the most fundamental concepts in quantum mechanics, and it has far-reaching implications for both the theory and practice of physics. By challenging the classical notion of determinism and introducing the idea of a probabilistic world governed by uncertainty, Heisenberg's principle forced us to rethink our understanding of reality, measurement, and knowledge. The principle reflects the wave-particle duality of quantum objects and highlights the limitations of our ability to measure certain properties with precision. It also challenges the classical idea of an objective reality that exists independently of observation and raises important philosophical questions about the nature of knowledge and the role of the observer. In practical terms, the uncertainty principle has had significant applications in fields like quantum computing and quantum cryptography, where it continues to guide research and technological innovation. Heisenberg's legacy endures, shaping the future of science and technology in ways that were once unimaginable. Heisenberg's uncertainty principle profoundly influences not only quantum mechanics but also how we understand the very nature of reality. The fourth keynote focuses on the departure from classical physics, particularly how Heisenberg's work challenged and replaced the deterministic worldview that had dominated scientific thought for centuries. Classical physics, rooted in Newtonian mechanics, assumed that if the position and velocity of an object were known, its future behavior could be predicted with perfect accuracy. The belief in a deterministic universe shaped much of scientific exploration. However, Heisenberg's uncertainty principle introduced a shift away from this certainty, highlighting the probabilistic nature of quantum systems, where outcomes are governed by chance rather than certainty. Classical physics offered the idea that with enough knowledge, we could predict any event with precision. For example, if you knew the position and velocity of a ball, you could forecast its path with exactness. This deterministic worldview extended to every aspect of nature. Newton's laws of motion provided an elegant framework where the present determined the future, and this view prevailed for centuries. It reinforced the belief that everything in the universe followed precise rules of causality, and that, theoretically, a sufficiently advanced observer could know everything about the system. However, Heisenberg's uncertainty principle disrupted this comforting belief by revealing that at the quantum level, certainty is impossible. The principle states that certain pairs of physical properties, such as position and momentum, cannot both be known to arbitrary precision simultaneously. This uncertainty is intrinsic to the nature of particles and does not arise from the limitations of measurement tools. The uncertainty principle suggested that at the quantum level, the universe does not behave in the neat, predictable manner that classical mechanics had promised. Instead of precise values, particles exist in states of probability, with various outcomes possible until a measurement is made. Heisenberg's work directly challenged the deterministic worldview by introducing the idea that nature at the quantum scale is fundamentally probabilistic. Rather than giving us exact answers, quantum mechanics provides the likelihood of various outcomes. For example, when measuring an electron's position, we can't pinpoint its exact location. Instead, we get a probability distribution, suggesting where the particle is more likely to be found. The more precisely we try to measure one property, like position, the less certain we become about the other, such as momentum. This is not just a technical inconvenience. It reflects the very nature of reality at the quantum level. The universe at its smallest scales does not operate like a machine with well-defined parts, but behaves in an inherently probabilistic way. The uncertainty principle has also led to new conceptualizations of knowledge and observation in quantum mechanics. In classical physics, an observer was considered a passive entity, simply measuring the state of a system without influencing it. In contrast, quantum mechanics suggests that the act of measurement itself alters the system. For example, when measuring the position of an electron, the measurement disturbs the system and causes the wave function to collapse, forcing the electron into a definite position. This introduces an active role for the observer, blurring the lines between subject and object and raising profound questions about the nature of reality. Does the universe exist independently of observation, or does it require observation to come into being? This question, rooted in the implications of the uncertainty principle, continues to shape philosophical debates about the nature of existence. In conclusion, Heisenberg's uncertainty principle represents a fundamental shift in our understanding of the universe. By challenging the classical deterministic worldview, it introduced the probabilistic nature of quantum mechanics and revealed the limitations of human knowledge at the quantum scale. The principle not only transformed physics, but also forced us to rethink the role of observation and measurement in defining reality. The departure from classical physics is one of the most important aspects of Heisenberg's work, and it continues to influence both scientific and philosophical inquiry to this day. Heisenberg's uncertainty principle focuses on the profound implications it has had on the nature of reality. Heisenberg's work, through the introduction of uncertainty at the quantum level, forced us to rethink not only how we understand the behavior of particles, but also how we perceive the very fabric of reality itself. This shift in perspective has led to new philosophical and scientific discussions that continue to evolve to this day. One of the central insights provided by the uncertainty principle is that at the quantum level, reality does not consist of fixed, determinate values for properties such as position and momentum. Instead, particles exist in a state of potentiality until they are measured. This realization challenges the classical worldview, where objects in the universe were believed to have definitive properties at all times, independent of observation. In classical mechanics, it was assumed that an object's position, velocity, and other physical attributes existed with certainty, whether or not they were being observed. However, Heisenberg's uncertainty principle introduced a new paradigm. Particles, such as electrons, exist in a superposition of possible states, and only when measured do they collapse into one of those states. Until that measurement occurs, their properties are fundamentally indeterminate, existing only as probabilities. This uncertainty is not just a temporary limitation of our measuring devices or a result of experimental error. It is a fundamental feature of the quantum world. The uncertainty principle demonstrates that the universe, at its most basic level, does not operate in the same way as classical systems. In classical physics, knowledge of the present state of a system allows us to predict its future behavior precisely. In quantum mechanics, however, the act of measuring one property of a particle disturbs the system and prevents us from knowing other properties with absolute certainty. This departure from determinism marks a significant shift in our understanding of the universe. making it inherently probabilistic rather than deterministic. Moreover, the uncertainty principle challenges the traditional concept of objective reality. In classical physics, the assumption was that the universe operates according to a set of fixed rules and properties, independent of the observer. In quantum mechanics, however, the act of observation is intimately tied to the reality we observe. The famous thought experiment of Schrödinger's cat illustrates this concept. Before observation, the cat is in a superposition of both alive and dead states, existing in multiple potential realities simultaneously. It is only when the box is opened and the cat is observed that it assumes one definitive state. In this way, quantum mechanics suggests that reality is not fixed and objective in the classical sense, but is instead influenced by the act of measurement. This idea leads to significant philosophical questions about the role of the observer in shaping reality. If the act of measurement determines the state of a quantum system, what does this imply about the nature of existence itself? Is reality something that exists independently of our perception, or does it require the observer to bring it into being? The uncertainty principle pushes us to reconsider the relationship between perception, observation, and the external world, raising profound questions about the nature of reality and our place in it. In practical terms, the uncertainty principle has had a lasting impact on various fields of science and technology, particularly in quantum mechanics and quantum computing. The principle introduces an inherent limitation in how precisely we can control and measure quantum systems, but it also enables technologies that exploit quantum mechanics in innovative ways. Quantum computing, for example, takes advantage of quantum superposition, where qubits can exist in multiple states at once, allowing quantum computers to perform certain calculations far more efficiently than classical computers. However, the uncertainty inherent in quantum systems means that researchers must find ways to manage and minimize the effects of this uncertainty while building reliable quantum systems. In quantum cryptography, the uncertainty principle is leveraged to create secure communication channels. In quantum key distribution, QKD, any attempt to eavesdrop on the communication alters the quantum state of the system, making it detectable. The principle thus ensures the security of quantum communication, making it fundamentally more secure than classical encryption methods. These practical applications demonstrate how Heisenberg's uncertainty principle has not only reshaped our theoretical understanding of the universe, but has also paved the way for revolutionary technologies with real-world impact. In conclusion, Heisenberg's uncertainty principle has radically altered our perception of reality, challenging the classical notion of a deterministic universe and introducing the concept of a probabilistic world governed by uncertainty. The principle suggests that, at the quantum level, particles do not possess well-defined properties until measured, and this has profound implications for both science and philosophy. By forcing us to rethink the nature of knowledge, observation, and reality, Heisenberg's work has inspired new lines of inquiry and technological advancements that continue to shape our understanding of the universe. Whether in the philosophical exploration of reality's nature, or in the development of cutting-edge technologies like quantum computing and cryptography, Heisenberg's legacy endures as one of the most significant contributions to modern science. Heisenberg's uncertainty principle focuses on the philosophical and interpretive impact of his work. Heisenberg's uncertainty principle not only reshaped our understanding of the quantum world, but also triggered deep philosophical questions about the nature of reality, knowledge, and observation. For centuries, science, rooted in classical physics, adhered to the belief in an objective, deterministic universe, where the laws of nature governed all phenomena with precision. The uncertainty principle, however, introduced an element of unpredictability at the fundamental level of nature itself, leading to a fundamental shift in how we perceive the world around us. At its core, the uncertainty principle challenges the very notion that reality exists independently of observation. In classical mechanics, the idea prevailed that objects had definite properties, position, velocity, and other physical attributes, whether or not they were being observed. An object's position or momentum was thought to be a fact of the world, existing regardless of human intervention. In contrast, quantum mechanics, as shaped by Heisenberg's insight, suggests that at the quantum level, particles like electrons do not have definite properties unless they are observed. Instead, these particles exist in a superposition of possibilities until measured. The act of measurement itself collapses the superposition into a definite state, bringing a particle's properties into being. This idea, known as the observer effect, has deep implications for how we think about the relationship between the observer and the observed. In the classical view, the observer is a passive entity, merely recording the state of the system. However, in the quantum world, the observer plays an active role in shaping the system's state. This raises profound questions about the nature of reality itself. Does reality exist in a definite state when we are not observing it, or does it only come into being upon observation? The uncertainty principle thus invites us to reconsider the concept of an objective reality. It suggests that, at the most fundamental level, the act of observation is inseparable from the reality being observed, challenging the classical notion that the universe operates independently of our perception. This shift from an objective reality to one influenced by observation leads to significant philosophical debates. One of the key questions that arise from the uncertainty principle is, what does it mean to know something? Classical physics operated on the assumption that knowledge was about discovering objective facts about the world, facts that existed independently of us. In quantum mechanics, however, knowledge becomes a much more elusive concept. The uncertainty principle implies that there are limits to what we can know about a system, not because of our measurement tools, but because of the intrinsic nature of the system itself. Knowledge, in this sense, is not about uncovering hidden facts about a pre-existing, objective world, but about understanding probabilities and possibilities. Heisenberg's insight forces us to accept that our knowledge of the universe is inherently incomplete and that there will always be aspects of reality that elude our understanding. The uncertainty principle also forces a reconsideration of determinism. Classical physics was grounded in the idea of determinism, the belief that the state of a system, at one point in time, fully determines its future state. If you knew the position and velocity of every particle in the universe, classical physics suggested, you could predict every future event. However, the uncertainty principle introduced an element of indeterminacy at the quantum level. It showed that there are fundamental limits to how much we can know about a system, making it impossible to predict with certainty the exact outcome of quantum events. This uncertainty in quantum mechanics doesn't just reflect a temporary lack of knowledge or technological limitations, but speaks to the fundamental nature of the universe itself. The principle demonstrates that some level of unpredictability is woven into the fabric of reality at the most fundamental level. This philosophical shift toward indeterminacy also led to the development of different interpretations of quantum mechanics, each attempting to reconcile the uncertainty principle with our understanding of the universe. One prominent interpretation is the Copenhagen interpretation, which suggests that the wave function, which represents the probability distribution of a particle's properties, collapses into a definite state when measured. This interpretation emphasizes the role of the observer and suggests that the act of measurement is what defines the state of a system. Another interpretation is the many worlds hypothesis, which proposes that every possible outcome of a quantum event actually occurs, each in a separate branch of reality. The uncertainty principle is central to both of these interpretations, and in fact, many of the philosophical debates surrounding quantum mechanics stem from the implications of Heisenberg's principle. The uncertainty principle also has implications for the nature of time. In classical physics, time is considered a continuous, measurable quantity, where past, present, and future events are all part of an unbroken, linear progression. In quantum mechanics, however, the uncertainty principle suggests that time, like other physical properties, may not be as easily measured or understood at the most fundamental level. This idea challenges our classical conception of time as something fixed and absolute, suggesting that the measurement of time, especially in the quantum realm, may also be subject to uncertainty. The uncertainty principle forces us to reconsider not just the nature of space and matter, but also the very concept of time itself, making it a less certain and more fluid concept than previously imagined. Heisenberg's work, through the uncertainty principle, opened up new avenues for exploring the nature of reality and knowledge. It led to the realization that quantum mechanics does not offer absolute, deterministic answers, but instead provides us with a framework for understanding the probabilities and uncertainties inherent in the behavior of subatomic particles. The uncertainty principle helped establish quantum mechanics as a probabilistic theory in contrast to the deterministic world of classical physics. This shift was not only a revolution in physics, but also a revolution in how we think about the universe. It suggested that, rather than a universe governed by fixed laws and absolute truths, the universe operates in a way that is inherently unpredictable and uncertain. In conclusion, Heisenberg's uncertainty principle has had profound implications for both the philosophy of science and our understanding of the universe. By introducing uncertainty into the very fabric of nature, Heisenberg challenged the classical view of a deterministic, objective reality. The uncertainty principle forces us to rethink the role of observation in shaping reality, the nature of knowledge, and the limits of human understanding. The principle has sparked numerous philosophical debates about the nature of existence, the role of the observer, and the inherent indeterminacy of the universe. It has also influenced the development of quantum mechanics, which, in turn, has led to revolutionary technological advancements. Heisenberg's work continues to shape not only our understanding of the quantum world, but also our broader philosophical views on the nature of reality itself. Heisenberg's uncertainty principle focuses on the ongoing relevance of the principle in modern physics and its lasting impact on technological advancements. Since its introduction, the uncertainty principle has not only reshaped theoretical physics, but also laid the foundation for a variety of cutting-edge technologies that rely on quantum mechanics. While the principle itself presents challenges in terms of measurement precision, it has simultaneously opened up new avenues for innovation. The uncertainty principle's implications continue to influence fields ranging from quantum computing to cryptography, quantum communication, and even fundamental research in particle physics. The uncertainty principle highlights the inherent limitations in the precision with which certain pairs of physical properties, like position and momentum, can be simultaneously known. This intrinsic uncertainty, inherent to quantum systems, is not merely a result of technological limitations, but is a fundamental feature of the universe at the quantum scale. While this uncertainty challenges our classical notions of determinism and predictability, it also paves the way for the development of technologies that harness the strange and probabilistic nature of quantum mechanics. Over the past few decades, these technologies have advanced significantly, transforming the way we approach problems in computing, encryption, and secure communication. One of the most exciting fields influenced by the uncertainty principle is quantum computing. Unlike classical computers, which process information using bits that exist in one of two states, 0 or 1, quantum computers use quantum bits or qubits. Qubits can exist in a superposition of states, meaning they can represent both 0 and 1 simultaneously. This ability to process multiple states at once allows quantum computers to perform certain types of calculations exponentially faster than classical computers. However, quantum computing also requires managing the uncertainties inherent in quantum systems. The act of measurement, as described by the uncertainty principle, influences the state of a qubit, making the design of stable and reliable quantum systems a major challenge. Despite this, researchers continue to make significant strides in building quantum computers that could revolutionize fields such as cryptography, optimization, and artificial intelligence. Another area where the uncertainty principle plays a crucial role is in quantum cryptography, particularly in the field of quantum key distribution, QKD. QKD uses the principles of quantum mechanics to create secure communication channels. The uncertainty principle ensures that any attempt to intercept the quantum communication disturbs the system, making eavesdropping detectable. In this way, quantum cryptography offers an unprecedented level of security compared to classical encryption methods. The ability to detect eavesdropping without compromising the integrity of the communication represents a major breakthrough in secure communication and has significant implications for protecting sensitive information in areas such as government, finance, and cybersecurity. Quantum communication also benefits from the uncertainty principle's unique properties. Quantum entanglement, a phenomenon in which particles become correlated in such a way that the state of one particle is instantly linked to the state of another, even across vast distances, allows for the development of technologies like quantum teleportation and ultra-secure communication networks. Quantum communication relies on the fact that any attempt to measure or observe the entangled particles disturbs their state, making it impossible for an eavesdropper to intercept information without being detected. This makes quantum communication a powerful tool for secure data transmission in the future, ensuring that information remains private and tamper-proof. In the realm of fundamental physics, the uncertainty principle continues to guide research into the behavior of subatomic particles. For instance, in particle accelerators like the Large Hadron Collider, LHC, scientists explore the fundamental forces of nature by smashing particles together at high energies. The uncertainty principle is central to understanding the behavior of particles at such small scales where quantum effects dominate. The principle also underpins the study of quantum fields, the search for new particles, and the exploration of phenomena such as dark matter and dark energy. These areas of research push the boundaries of our understanding of the universe and could ultimately lead to discoveries that alter our conception of the cosmos. While the uncertainty principle is most often associated with quantum mechanics, it has applications that extend beyond physics. In fields such as biology, chemistry, and even economics, the uncertainty principle serves as a reminder that uncertainty is inherent to the natural world. In biology, for example, quantum effects have been observed in processes such as photosynthesis, where the behavior of particles and energy transfer at the quantum level plays a role in optimizing energy efficiency. Similarly, in chemistry, the principle helps explain molecular interactions and the probabilistic nature of chemical reactions. Even in economics, where uncertainty plays a central role in decision-making and market behavior, quantum concepts inspired by the uncertainty principle are being explored to model complex systems in more nuanced ways. The ongoing research into quantum technologies and their applications is a testament to the lasting impact of Heisenberg's uncertainty principle. despite its initial challenges to classical physics and the discomfort it caused among many scientists. The uncertainty principle has proven to be a valuable tool in advancing our understanding of the quantum world and developing technologies that are reshaping industries and society. While the uncertainty it introduces into our measurements may seem counterintuitive, it has also inspired innovation by encouraging us to think beyond the confines of classical determinism and embrace the probabilistic nature of the quantum realm. In conclusion, Heisenberg's uncertainty principle continues to shape the future of science and technology. It has fundamentally altered our understanding of the universe at the quantum level, introducing an element of unpredictability that challenges our classical notions of determinism. The principle's influence extends beyond theoretical physics into practical applications, including quantum computing, cryptography, communication, and fundamental research. As scientists continue to explore the quantum world, Heisenberg's legacy will remain central to these advancements, providing both the foundation and the challenges that drive the pursuit of knowledge in the ever-evolving field of quantum mechanics. The uncertainty principle is no longer just a theoretical concept, it has become a cornerstone of modern science and technology, helping to shape the future in ways that were once unimaginable